All right, let's dive right into this explainer. We're going to be looking at the totally complex and honestly super fragile machinery of human memory and the wild medical mysteries that accidentally revealed its secrets to us. We all kind of take our memories for granted, right? We wake up knowing exactly who we are, where we live, what we did yesterday. But the actual biology making that mundane morning routine possible, it's incredibly intricate. So today, we're unpacking the neuropsychological basis of learning and memory, and we'll look closely at the extraordinary, really dramatic medical cases that literally mapped the human brain for us.
Let's start with this vivid description from John Hamilton. Quote, "It's a sense of flooding the brain too quickly. The brain has this disruption, and the short-term memory isn't converting into long-term memory." End quote. This brilliantly captures the sheer terror of a brain struggling to hold on to the present. Just imagine that feeling for a second. An endless flood of new information, new faces, new experiences rushing at you, but absolutely nothing sticks. Your mind is trapped in a permanent present tense, all because that vital bridge between what you're experiencing right now and what you'll remember tomorrow has just completely collapsed.
Which brings us to a really compelling medical mystery. How do we actually learn? And what happens when the very biological hard drive recording our lives is permanently broken? The stakes here are absolute. Without that system, the narrative of who we are just stops. To understand how we avoid this fate, we have to look to cognitive and experimental psychology. Specifically, we look at what happens during amnesia. By seeing exactly what's lost during brain damage, we can actually work backward to understand how a normal, healthy memory functions. It's like reverse engineering the mind.
To solve this mystery, we first need to establish a baseline. So Section 1, how memory actually works.
So the absolutely crucial point here is that learning is the process, and memory is the permanent outcome of that process. People throw these two words around interchangeably all the time, but in neuroscience, they're completely distinct. Learning can happen almost passively. You might remember the details of someone's face just by seeing it on your commute every day without ever, trying to study it. But memory? Memory is the actual concrete evidence that the learning stuck around over time.
Now, the way this works is by breaking memory down into 3 distinct sequential stages. It's almost like taking a mental photograph, filing it away in a cabinet, and pulling it back out later. First up is encoding, and this actually has 2 subphases. Acquisition, where your sensory buffers grab that raw input, like a sight or a sound, and consolidation, where the brain goes to work creating a stronger, stable representation of it. Next is storage, which locks in that permanent record in your neural networks. And finally, retrieval. That's your ability to actively pull that stored info back up, whether it's recalling a memory or riding a bike. But here's the kicker. If any single one of these 3 steps fails, that memory is gone forever. To understand where our knowledge of these exact steps came from, we have to jump back in time. Section 2, the era of radical surgery. So back in the mid-20th century, doctors were experimenting with some wildly radical brain surgeries to treat severe diseases. It was just a totally different era of medicine, driven by, frankly, a lot of desperation. Faced with debilitating conditions that didn't respond to any drugs they had, surgeons were trying massive, highly invasive procedures. We're talking prefrontal lobotomies, severing the corpus callosum, temporal lobe resections, often scooping out whole sections of the brain without having any real clue about the long-term biological consequences. And these procedures, usually totally by accident, ended up cracking wide open a brand new window into how human cognition is actually wired. And this wild era of experimentation leads us directly to Section 3, the case of patient HM. This story is incredibly tragic, but it is hands down the most famous and illuminating case study in all of modern neuroscience. In a desperate bid to cure his worsening epilepsy, HM underwent a really radical surgery. His seizures had been getting violently worse through his teens and 20s, and the drugs back then just weren't cutting it. Neurologists mapped his brain and figured out the seizures were starting in the medial portions of his temporal lobe. So in September 1953, a surgeon named William Beecher Scoville went in and removed the medial temporal lobe on both sides of HM's brain. And the crazy thing, the surgery was a massive success for his epilepsy. It completely stopped the seizures. But it left this shocking side effect that his doctors and family quickly started to notice.
And this brilliantly illustrates the absolute tragedy of his condition. In April 1955, patient HM was actually 29 years old, but he genuinely, truly believed he was only 27. A full year and a half had passed since he was wheeled into that operating room, but his mind hadn't recorded a single solitary day of it. He was profoundly amnesic.
Okay, let's dive into the bizarre paradox of HM's brain. He completely retained his high intelligence. He could remember his childhood, and he could hold a sharp, witty conversation with you right there in the room. But the absolute second you stepped out the door, he would forget he ever met you. This wasn't that Hollywood amnesia where someone forgets their own name. HM knew exactly who he was. His IQ tested well above normal, his language skills were totally flawless, and his short-term working memory perfectly fine. The deficit was literally just one highly specific thing. The transfer of information from short-term to long-term memory was permanently severed. He simply could not acquire and store new information. With his short-term memory totally disconnected from long-term storage, scientists had to find out exactly what part of the brain caused this. That brings us to Section 4, isolating the hippocampus. So HM was suffering from anterograde amnesia. That's a severe inability to form new memories moving forward in time. For decades, scientists relied on Dr. Scoville's surgical notes, which basically said, yep, all of HM's hippocampus in both hemispheres is gone. But fast forward years later, when high-resolution MRI scans became a thing, researchers went back and looked at HM's brain again, and they found a massive detail. The surgery hadn't just taken out the hippocampus, it had actually scooped out some of the surrounding cortex too. So this left a massive elephant in the room. Was the hippocampus itself the golden key to forming memories, or did that surrounding brain tissue play a role in his amnesia? To figure this out, the scientific community desperately needed another case study. They had to find a patient with damage strictly limited to just the hippocampus and absolutely nowhere else.
Well, they finally got their answer by comparing HM to a brand new patient known as patient RB. Now, RB developed the exact same anterograde amnesia, but his damage was microscopic. It was isolated strictly to this tiny, specific layer of tissue inside the hippocampus called the CA1 pyramidal cells. Basically, RB had suffered an ischemic episode, a severe drop in blood flow to the brain, during a heart bypass surgery. And just like HM, he woke up with this dense anterograde amnesia, no new long-term memories. When RB later passed away and generously donated his brain to science, the neuroanatomy revealed something incredible. His lesions were entirely restricted to the hippocampus. His case perfectly isolated the variable that HM's messy surgery had obscured. This takes us to Section 5, the geography of memory. The conclusion from comparing these cases was absolute. Without a functioning hippocampus, your brain's ability to consolidate temporary experiences into permanent records is totally 100% lost. Patient RB's microscopic damage definitively proved that the hippocampus is the main engine for creating new long-term memories. It is the vital bridge that connects that fleeting, short-term sensory stuff to the permanent storage architecture of your brain. Think of the brain's division of labor kind of like this. The hippocampus is the printer actively creating the files, but it is not the filing cabinet itself. And this perfectly explains why older memories are totally safe, even when the hippocampus is destroyed. See, patients like HM and RB also had a little bit of retrograde amnesia, meaning they forgot some stuff from right before their brain damage, but it was limited to just a year or two. Their childhood memories, their teenage years, perfectly intact. This was a huge realization. It proved that long-term memories, once they're fully consolidated over a couple of years, get shipped out and stored in the wider cortex, completely independent of the hippocampus. As we wrap up this explainer, I want you to consider this. Every single experience you cherish, every face you learn, every new piece of information you take in, it's all completely reliant on a tiny, fragile little structure deep inside your temporal lobe working flawlessly in this exact second. Without the hippocampus, the present literally just vanishes. It's such a profound reminder of the delicate, intricate machinery that makes us who we are. So what are you going to do with the memories you're forming right now? Keep learning, keep questioning, and until next time, thank you so much for exploring with us.